Hello. Am I audible? Okay, thank you for the introduction. Your mic was muted at the end. So, anyway, so I can start the presentation. Shall I start my presentation, right? Okay. So, thank you very much for the introduction and thank you for giving me the opportunity to talk about an emerging topic of geotechnical engineering. This is a faculty development program, so I guess there is a good knowledge about the basic geotechnical engineering. And when we talk about classical geotechnical engineering, we mostly focus on its strength behavior, which is mainly useful for roads, embankments, compressivity behavior, etc. Uh, so, as the theme is for emerging geotechnical engineering, so this is one of the topic which is there are a lot of research is going on, and I thought to give you a brief idea. At least in a session we cannot learn in deep everything, but I'll try to give you a overview what it is and what are the type of research is going on and what are the future scope, challenges, etc. Okay, so with this will share my screen. Yes, is it visible? Okay. So the topic as I gave is the containment of high-level radioactive waste and opportunities and challenges to geotechnical engineers. So usually, as I said, when we talk about the geotechnical engineer, initially it started with uh, foundation design, then roads, then embankments, etc., etc. Then as time progresses, there are a lot of waste which is generated from different industry, and in order to take care of this waste, I think I may switch off the video. Just one minute. So one of the major challenges in the near future is to take care of the different waste. That is different municipal solid waste from various industries, even waste coming from our household. Everything is a new challenges for the environment and for the engineers. So one of these is the radioactive waste. So I would say due to the pandemic, we have got more opportunity to learn, because previously when we were in undergraduates or we were learning, we did not know about this kind of topics and what are the opportunities which can happen. So there has been pandemic, but due to this online learning and all, we are more frequently listening various lectures and getting some knowledge of the different things. So when you talk about the radioactive waste, it is basically defined in the terms of three different radioactivity. One is low level radioactive waste, one is intermediate level radioactive waste, another one is high level radioactive waste. And we usually use this kind of radioactive waste in our day-to-day life, but we do not bother too much about the small scale radioactive, which are low level radioactive waste. For example, if there is some list here, you see low level radioactive waste, which are cleaning rags, mops, filters, medical tubes, so many things which you use. Even for research, we use some kind of radioactivity. A cancer patient, they are given some radioactive treatment. Those are not very high level radioactivity, okay, and which actually have around 90% of the volume worldwide, and the radioactivity is only 1%. Then another type of radioactivity waste, which is known as the intermediate level or medium level, which is also from different ion exchange resins, some sources in radiation therapy, etc. The overall volume is only 8%, and the product produce only 44% of the radioactivity. So these are the small level or intermediate level where when you want to dispose it or you want to throw away, we need to take a little bit of care, but it is not that much harmful. The most important thing or most challenging thing which we need to take care is the high level radioactive waste. So when we talk about the high level radioactive waste, it is the byproduct of the reactions that occur inside nuclear reactors. So as you know, there are a lot of nuclear power plants. We cannot live without power nowadays, without mobile phone, without charging. Even now we are all connected through a virtual mode, but without electricity it is not possible. So most of the electricity comes from our coal-fired thermal power plants. There also one ash is generated, fly ash. That is also another important challenging aspect to how we can utilize it, how we can contain it properly. Similarly, there is another one which is nuclear power plant. So from the nuclear power plant, whatever waste is generated, that is the very, very high level toxic waste, and which radioactivity also is for very long time. They don't decay it so quickly. Okay, so it takes hundreds or even thousands of years to decay the radioactivity. Okay, the overall volume of this only 2%, but it contains 95% radioactivity. So that's why we need to understand. We know there are a lot of examples of nuclear atom bombs were dropped and what happened to the human beings, and the entire population of everybody died. So in order to protect ourselves from such situation, when the waste is generating from the power plant, nuclear power plant, we need to dispose it properly. And I'm sure very few people of us we have this kind of idea of how it is disposed and what are the plans. So this topic is mainly to talk about how this kind of waste is contained and what, as a civil engineers or geotechnical engineers, is our role. This picture, if we see, I hope screen is visible and if it is audible to everyone. If there is any problem, please let me know. And yeah, and in case anybody has any doubt, you can stop and ask me question. As I'll try to explain as much as possible. So if this picture is for nuclear fuel cycle, you can see in the very first one, it's the uranium mines and mills from where we get the raw material, that is uranium, thorium, which actually produces this nuclear energy. So just imagine someone is going to a mine, they are digging it and taking out that uranium. At the time, nothing is happening, isn't it? That's the raw material which we are bringing to the nuclear power plants, where we are using the physics, doing fission and fusion, we are extracting the energy. After that, it becomes so charged up that its radioactivity can destroy entire humankind. So that means initial stage when you take it out, the radioactivity is not that much. Then you are converting into oxides and then conversion to fuel. After that, the fourth stage when it is in the reactor, their reaction is taking place. You extract the energy, generate electricity. Then you can reprocess it. If there is some more energy is available, you reprocess it again to extract more energy. Then it goes to the waste management, waste storage, and some byproducts may be produced which can be used in medicine, agriculture, etc. So then after waste management, you can recover and you can try to reuse again. So this is the stage where our geotechnical expertise is required when we are doing this waste to store or we want to dispose, what we can say. This table is to show how the radioactive waste, what are the different forms and what kind of treatment can be done. LL for low level radioactive waste, which I told in the beginning. IL is the intermediate level and HL is the high level. This can be either in the liquid phase or solid phase and in the gaseous phase. If it is liquid waste, what can be done? You can do either chemical treatment, you can do ion exchange, reverse osmosis, evaporation. These are the methods to reduce its radioactivity as much as possible. Once you use it, before you dispose, once you go for disposal, there are also a lot of financial things involved. So if you can reduce the volume, if you can reduce the radioactivity, then the amount of money involved also will be less. You need to less the amount of precautions to take care. This can be either in the waste, solid waste form, or you can do compaction, incineration, pregnancy and repackaging. These are the different techniques which are intermediate process. We are actually not involved in this. Mostly physics and chemistry, those are involved. But also it can be the gaseous phases also. Finally, what our requirement is, all these intermediate processes when are done and we cannot do any more treatment, then we go for this disposal. Here there is one stage called interim storage. So when the waste comes from the power plant, which is high level toxic waste, you can imagine the temperature will be order 1000 degree or 900 degrees centigrade. So at the moment you cannot dispose it anywhere. If you dispose it immediately, there will be fire. Even if you put inside the soil will burn and it will be like a brick, something like that. So internally you have to keep it in somewhere and cool it down. You apply water for a very long time so that it cools down, and then you have to throw it out, that dispose it. So and this disposal part is where, as the geotechnical or civil engineering, we have the role how to dispose it. One is, you can see the literature, deep geological disposal, reinforced concrete trenches, earth or soil stone lined trenches, okay, tile holes, all these things comes under civil or geotechnical engineering. So once you dispose, then you have to regulate it for a very long time, whether there is any effect to the nearby water body, soil, vegetation, waste management, etc. And monitor environmental for very long time. You see it's written, institution control of near surface disposal facility for 300 years. So once you dispose high level radioactive waste, you have to look there for it that at least 300 years all this is intact. In case there is any problem, you can just imagine there is always dumped in Raurkela city somewhere. Some dogs are going there, some pigs are going, and they are throwing away here and there all this waste for radioactive waste, you cannot do those kind of things. It is as critical as generating thermal energy from this oil. I mean, thorium, uranium, etc. So the place should be entirely confined. Nobody should enter. There should not be any interference, and you have to put monitoring stations to check whether there should not be any contamination. Now, this is a typical uh, waste containment liner system, where if you have the low level waste which are actually kept inside, and there is a clay barrier all over it, there may be some gas generation, gas you can collect and you can use it for some other like purposes. So small scale, low level or medium level waste, or medical waste, even municipal waste in the Western country or developed country, they follow this kind of techniques for containment of the low and intermediate level of the radioactive waste. So the title I have written, disposal technique for low and intermediate level waste. So it is same as like the municipal solid waste. Many of you, those who have studied geoenvironmental engineering, or you will listen the other talks by other experts, this kind of figures you will see. But when it comes to the high level radioactive waste, this is not actually applicable. So this is one of the real life pictures, which is called near surface disposal of low level waste. You can see some sort of drums where we put some oils or kerosene. Inside this is placed, and you have got the concrete all over it. You cover it also with the concrete, and you designate an area and dispose there. So this is some kind of facilities for the low level waste. There is some work going on for construction of this kind of low level waste. These are real life pictures where this disposal takes place. And disposal technique for high level radioactive waste. So what are the sources I already talked about? Mainly we were talking about the India. There are globally it's a emerging problem, and the research is going on for throughout the world. So there are nuclear power plants in India. This is the picture where the small map is given, the nuclear power generator. As per 2018, India has 22 nuclear reactors in operation in 7 nuclear power plants with total installed capacity of 6,780 megawatt power. India generates around 4 tons of nuclear waste per gigawatt annually. Now, for this case, what is the solution globally? So, initially, when the nuclear power was generated, there are a lot of things were thought of by the scientists how to manage this waste. So, one was the deep sewage disposal. That means you put it inside a canister or inside a container and take it through a submarine to the very deep of the ocean and place it there. That was one of the trials. What was found that if they dispose there, that is actually causing problem to the flora and fauna inside the sea. So that is for long term, that is not good. Even if you put inside a canister, let's say it's a steel or copper or anything, it may corrode inside the water for up to some time, and that radioactive waste can come out and it can cause more harmful effects on the fish and plants, etc. Then again, it was thought at the polar ice sheet disposal. So you take it to the poles, North Pole or South Pole, and place it inside that ice. But that was also not very feasible because ice may melt, and that can cause problem to the flora and fauna system of the poles. Then the final concept which in which research is going on. Even some countries have started the disposal of the radioactive waste. This is to give you information that all the radioactive waste which is generated throughout the world, only one or two country has started disposing it in a disposal place. Rest all the country they are simply storing it. So you can imagine how much storage space is required, and everybody is in a research stage to dispose properly. So there are a lot of research opportunity at this moment. In India, their plan is India may start disposing all this waste in 2050. Okay, so last 50, 60 years, whatever nuclear power plants we have developed and the waste which is coming from the nuclear power plants are still kept. It is not thrown away anyway. It is not disposed. So DGR means Deep Geological Repository. E for deep, G for geological, and R for repository. The Deep Geological Repository we'll talk about later on. But when we, as I said initially in that figure, that we are taking out raw material, uranium, thorium, then we are processing it, and after fusion, it become very harshly radioactive. So if we do some kind of reprocessing, this radioactivity may decay. In this graph, if you see, on the right hand side is the x-axis is for number of years it can take for radioactive decay. The blue line, horizontal line, you see it's the toxicity of equivalent amount of uranium ore, so which we take out from the mines. And the red or brown color is the spent fuel. Spent fuel means the fuel which is coming out after radioactive fusion from the nuclear power plant. And then researcher thought, so if you see the intersection between these 2 points, which is around 1 lakh years, 100,000 years. So the fuel which is coming out, which we get as a waste from the nuclear power plants, if you keep it for 1 lakh years, that will reach to the radioactivity or toxicity level of the uranium ore after 1 lakh years. Then if you still reprocess, it can come down to that another line where you can say HLW, which is between 1,000 to 10,000. This one, again, to give you a better idea. So initially, radiotoxicity of uranium ore is somewhere here, the line which is given as 1. Waste after reprocessing without partitioning it from 1 lakhs, it can come down to 10,000. Then again, scientists started doing to extract some more energy by doing some kind of called partitioning, which is some physics things. It comes down to 300 years. So at least we have to ensure that the waste disposal facility which you are making is safe for 300 years. Normally, as civil engineer, when we construct a building or anything, we consider its lifetime is around 40 years or so. But here it is minimum 300 years. Earlier it was to consider as around 1,000 years, but now due to development of further development, at least 300 years it should be safe. So this is the overall management facility, reactors, spent fuel, the interim storage where you cool it down, then again reprocess, and this is the high level waste which actually bring it down to the disposal place. This is the Deep Geological Repository. The scheme of Deep Geological Repository concept, or DGR, which I talked about, and this is where the challenge is, and this is what I am going to talk more. So why it is called Deep Geological Repository? Deep means It is around 300 to 1000 meter deep. So from the ground level, you can see with this schematic diagram, the top one is to ground surface facility or where we are staying, human beings, buildings, etc. Then a tunnel is created at the bottom below the ground level inside a rock, and there those radioactive waste are disposed in the form of trenches. You excavate the trench, place them, and cover it with the soil. Okay, so that soil is used, which is known as the expansive soil or bentonite. So here the geotechnical problem comes. The first geotechnical challenge is when you are constructing such a big tunnel below the ground, that itself require huge engineering. You need to have huge machinery. There should not be rock failure takes place. You need to take care of the pore pressure, all these classical soil mechanics. Then comes here to place those radioactive waste which radiate a lot of heat. Ultimately, after reprocessing, it cools down around 100 degrees centigrade temperature. So in the normal classical geotechnical engineering, we don't talk about much about the temperature. Here, temperature also is another important aspect, how this temperature is radiating from this waste to the surrounding geological media of soil and rock. And when it fills with the gaps are filled with the soil, whether that soil is fulfilling the properties or not. Now, if we take a bigger picture of this, this is known as the disposal tunnel. So this brown colors, what you can see, this is the disposal tunnel. And the red color, this is known as the canister. Canister means the kind of drum picture I have shown, which can be made of steel or copper. So inside that, you keep the waste fuel in the compaction form. You compact it and keep it inside. Then this is the host rock. Okay, so and that is the canister containing the fuel, and the gap between this canister and the rock is filled with the bentonite based buffer material, or this is the expansive clay. That is where our geotechnical engineering research is going on in this material behavior. So globally, it has been accepted that we should use the bentonite based barrier material because it has got certain property which is very low hydraulic conductivity. It may absorb the radioactive waste in case there is some kind of failure. It can form bonding and it retards the movement of the particles, and it expands a lot. So it has got some soiling property which can seal all these gaps. If we take another bigger picture of this, you can see this is the host rock, this is the disposal sand tunnel. So inside the rock, first you excavate. Excavation takes place, and these are the bentonite blocks or the expansive clay in compacted form. You make it like a big annular sort of ring is formed actually in the field. Then you fill it with a waste canister. Okay, so this canister is nothing but it's a container which contain the radioactive waste, and it can be either made of copper or steel or aluminum, mostly either copper or steel. Then you fill it, all around is the bentonite brick. So as geotechnical engineer, our role is to look at, first of all, like this excavation part, the inside the rock, and then the property of this bentonite block. You can see it has got a very important role. Now you have got such a high level radioactive waste, and here is the rock which may have certain kind of some water due to saturation at certain level. Also, there is a huge overburden pressure of such depth, so it should not fail easily. if there is some failure of this block, it can affect this waste canister. So if this canister breaks or some kind of failure takes place, the radioactivity can come to the these rocks and surrounding media, through which it can go to the drinking water, it can reach to the many places. Okay, it should not. So this bentonite blocks has got very low hydraulic conductivity. If the water which is coming from the rock, it can have some salts also. So salt and water, when it reaches to steel or copper, it can corrode the material. So with time, when you are thinking of the 300 years to 1000 years, that corrosion may actually cause damage to the canister. So you have to look at all these properties. Also, it has got around 100-degree temperature. So these bentonite blocks should not behave differently at such temperature, that we need to ensure. We need to compact it to that level so that all these properties are fulfilled. So this is to show that from the canister, temperature is flowing or heat is flowing out towards outside, and the water is actually gradually coming in. This is says that technological gas filling. That means you're making an excavation inside a rock. Obviously, this won't be as smooth as it is shown in this figure. There will be some small gaps. So through those gaps, gradually water may penetrate, some salts may come, and if it comes in contact with the canister, gradually it will corrode. But because of this unique property of the bentonite, which contains montmorillonite or expansive clay, once some water comes in, it will fill the gaps, it will expand. Montmorillonite is nothing but, I think there are a lot of girls here, it is the multani mitti which we apply in our faces for different purposes, I mean for makeup and all. Okay, so that's the actually the bentonite, which is nothing but the volcanic ash. And in India, mostly it is available in Rajasthan, Kashmir, and some places. So once it in contact with the water, it expands a lot, and all these gaps are filled in. And with time, radioactive decay will take place. Also, everything will getting saturated. So these are the different salts or different which may contain sodium, calcium, etc. This is another picture of the geological disposal concept. Okay, and every country is now in the phase of research who are producing radioactive waste. Or some countries like USA, Sweden, they are in the very forefront of the research, and they are about to dispose their radioactive waste. So here it's a bigger picture. You can see this is where the surface facility, the tunnels are made, and these are the trenches. Inside the trench, the radioactive waste are disposed. So you can see these are the mainly 0.5 meter by 0.1 meter, which are filled inside the canister. So this is the used fuel container or container canister. There are a lot of such kind of fuels are kept inside, and then these are the bentonite clay and surrounded by rock. So we mainly look at the property of this bentonite clay under these different conditions. First of all, high temperature, water migration through the rocks, which may contain salt, and huge overburden pressure. So with this condition, whether they are fulfilling all the as possible, all the criteria or not. This is another picture which is mostly taken care by India. Same thing. Canister is called overpack, buffer, backfill, disposal pit, disposal tunnel. More or less all over the countries, the concept is more or less same. But the material, the rock, which are not same place to place, the property of the rock will vary. Place to place, the property of the bentonite or the clay which is available locally. You cannot bring your this bentonite or clay from USA or Australia because that will be huge costly. So we need to use the locally available material. This is not a small area. Huge number of barrels or canisters will be kept. So we need to do research on the locally available material. These are some of the pictures uh, which is in France and Barcelona. What they have done, they have constructed the laboratory at about 300 to 500 below the ground, and they are trying to understand. They have tested for 5 years, 7 years using this bentonite material under different temperature and the pressure, whether any properties are changing or not. So these are actually the bentonite bricks, which are kept in like a tunnel, and we expect that heat will be generated by the radioactive waste. So this is another test where you can say in the middle some wire is coming out, a metal heater is placed. Okay, so we use the heater for different purposes as cooking and all. So you place a metal heater and place these bentonite blocks around, and there are a lot of sensors to check like the thermal conductivity. In normally, as I said, in classical geotechnical engineering, we don't bother about the thermal property, but here thermal conductivity is one of the important aspects which to be determined and to understand at different conditions, different water content, different temperature, how this thermal conductivity is changing. Also, it has got hydraulic conductivity is one of the important parameter, whether it is changing with time or not. So these are the large scale testing which is being done in different places in Spain and France. These are also some of the real life pictures when you want to excavate tunnels or when you want to place the containers, how this excavation is being done and gradually how the bentonite blocks on everything is placed. You can see creating this machinery itself and taking down such a huge down underground ground itself one of the major challenging project. So what is the advantage of this concept? Why people did not go for other things? The principle of deep geological disposal is to confine and isolate HRW from surrounding environment over a long period of time up to 1000 years. The possibility to store large quantity of waste, you can store a large quantity of waste. It is relatively more economical as compared to other methods. And once the facility is closed, it will not require any more human intervention. You completely close it, you don't need to bother, but you need to put some kind of monitoring stations so that it is not affecting the nearby water bodies or the environment. This is the global status, how the globally it is some countries which are in the forefront in terms of this research. And these are the responsible in the agencies. Like in India, it is regulated by Atomic Energy Commission, and under them, Hava Atomic Research Center, they are working and they are the main regulatory body. Similarly, in Finland, the responsible agency name is POSIVA. They have received the construction license in 2015, but still it's just going on, not a completely disposal started. China, they plan to do the disposal in 2050. Japan, a detailed geological map including exclusion areas was released in 2017 for public review and discussion. So this kind of projects, let's say if I say I want to construct a nuclear waste disposal barrier in sector 2 of Rourkela, immediately there will be panic. People will start shouting, why in my area, why this, why not somewhere else, etc., etc. So a public review and discussion is required. So that first of all, choosing the site or site selection is one of the important thing. And so once the site has been selected, many countries they take the public opinion, and that is considered. In India, it is the Atomic Energy Commission, and the plan is to dispose by 2060. In Sweden, it is taken care by Swedish Nuclear Waste Management Company, and license application submitted in 2021. So similarly, different in UK, it is in the planning and selection site, etc. USA, they actually started filling the waste disposal repository with the nuclear waste in the Uaca mountain, but there has been some problem and they have also stopped it. So you can understand simply selecting the site itself is very challenging, and then fulfilling all the criteria required. Actually, final regulatory authorities, International Atomic Energy Agency (IAEA), which is based in Geneva. So there are a lot of researches going on, and the current status is, you can see, almost it is in the research area. So India also is doing a lot of research through Bhabha Atomic Research Center. Finland and Sweden are the first two nations to build and operate such repositories. Both the countries have highly convincing geological database to generate favorable opinion among general public and geological fraternity. Around 9,000 tons of spent fuel is forecasted to raise from Swedish nuclear fuel program, corresponding to roughly 4,500 canister in KBS3 repository. Disposal concept, in which copper canister with a cast iron insert containing spent nuclear fuel are surrounded by bentonite clay and deposited at approximately 500 meter depth. So mostly around 500 to 1,000 meter depth, all the countries have planned to dispose. In Indian nuclear disposal program, this is the picture of one of the gold mine in Karnataka, where some kind of test conducted using the bentonite clay and generating the temperature which is expected in the nuclear disposal repository, and there is a lot of parameters which are tested. A oil-defined program already is in place. The first underground field-scale in-situ heater test of 6 years duration. So test conducted for 6 years. You cannot do any test for 1,000 years or 500 years. That's not feasible. Practically, if we are doing a PhD, usually it is considered 4 to 5 years. So you need to do so many PhDs to have the total idea, and you cannot continue your test or examination for years and years. You can do it for a few years, and then you can do a modeling, use a numerical model or computer models to understand its behavior for so many years. So this is one of the tests which was done in Indian Karnataka. So major role of geologist. This repository actually require multidisciplinary people. You need physics people, you need geologists, you need mechanical engineer, you need electrical engineer, you need geochemist, everyone. So during building a DGR, geologists are often expected to select a suitable site having desirable geological, structural, hydrogeological, geochemical, and rock mechanical characteristics. So the rock which you are selecting to dispose, they should fulfill the criteria also. You should select a site which is less prone to earthquake. In India, there is a map which gives the earthquake prone areas and less earthquake prone areas. The total area has been divided into four different zones, zone 2 to zone 5. Zone 5 has got the highest earthquake prone, and zone 2 is the less. So you have to select or choose some places where there is the least chance of earthquake, because if earthquake happens, it may broke everything and it can dispose all the radioactivity. Site selection is followed by large scale characterization. So after you select the site, you need to do large scale characterization to understand the site response in terms of long term structural stability, groundwater regime, etc. These two phases in any national program involve almost 20 to 30 years. Okay. The numerical study of the research conducted by Bajpai and Singh, they are the researcher in Bhabha Atomic Research Center, proposed granites with good mechanical strength and thermal conductivity can provide a stable DGI. So, based on their research, that it has been proposed to use our Indian nuclear waste disposal facility in the granite rocks. This is some pictures of the vitrified waste in the interim storage condition before it has been disposed to the final disposal. This is the layout of the Indian disposal repository, same thing which already I've shown several pictures. So in the Indian nuclear disposal program, waste disposal program, initially it has been planned to have 10,000 overpacks. That means 10,000 canisters to place in the disposal facilities. And as per the site selection is concerned, it has been planned probably in the desert areas of Rajasthan, so that in case there is any issue, it will not affect the human being. Now here I am going to talk about the geotechnical aspects, or what is our role. As I already said, the bentonite is chosen as the material that will be placed in between the canister or the container which contain the radioactive waste. After the container is placed in between the rock and the canister. So that has got a lot of things to do. One is, so it is known as the buffer material. So buffer material is the material in the immediate vicinity of the waste container. Also, there is a term called backfill material. The material proposed to be used to seal the galleries after placement of waste container. So if I go back to the previous pictures, yeah. So here you see, this is the overpack, or this is the waste which is filled with the buffer material. So similar such, if you say this figure, in a row maybe 500 number of such tunnels are created and those are placed. This disposal tunnel, that is also you need to fill up. Like when you do mining, in coal mines, we take out the coal and we fill it with the soil. Otherwise, there may be a collapse. So once the radioactive waste is placed, the tunnels which are there, that has to be filled in also. And there it is filled with the bentonite as well as the sand mixture. That is known as the backfilling material. So why bentonite is chosen as the material? Because of its low permeability. So normally sand, it has got the very high permeability. Water will percolate immediately. Whereas clay has got the less permeability. Bentonite is one of the clay which has got high amount of monzonite. Monzonite is one kind of mineral which attracts water and it forms diffuse double layer, and the flow of water is retarded. So the permeability is very less. So if you consider that a host rock has got a lot of water which can percolate and it can reach to the canister, it retards that for a long time. Then self-filling. Self-filling means in case there is certain gaps when water is enters, it will automatically expand and it will fill it. Or in case there is a temperature, it evaporates the water and there can maybe some cracks from. But as soon as the water comes again, it will expand and those cracks which are developed, it will automatically heal or automatically fill in. That is why it's known as the self-filling. Also high soiling capacity. So because of its high soiling capacity, the self-filling takes place, and also it retain the cations and ions. In case thorium, cesium, all this radioactive material is come out, it will form a bonding with those and deter the movement of those material. That is why the bentonite has been chosen. We could have choose cement also. Cement also has got less permeability. You can just simply fill it with the cement concrete. But cement concrete, in case there is any crack, it will automatically never fill. The gaps which is between the rock and the concrete, in case there is certain gap, that will also never be filled in. But this bentonite has got the unique properties. It can automatically fill such gaps. It can also take care a lot of overburden pressure if you compact it. That is why this material is the best material chosen for this purpose. So why this bentonite material is chosen, I just want to show you this picture. Those who in the classical soil mechanics class, we studied this mineralogy. So this is the first one is the unit layer of monzonite, which is nothing but a 2:1 mineral. Now this material is compacted to very highly dense and dense like a brick. Okay. So once you compact it, the particles is arranged together and they can attract huge number of water molecules. So here it is written 3 to 50 layers. Okay. In between two layer of monzonites, they can attract a lot of water. And because of that, you have got two layers, and if water is trying to enter, what will happen? And if you do not allow it to enter, it will try to expand and it will push back. So some kind of pressure will generate. That is called the soiling pressure. Because of this nature, it develops a lot of soiling pressure. So as an engineer, we need to find out the optimum value of this soiling pressure. We cannot allow to expand is as much as possible, then it can even break the canister. Okay. So you can study about the monzonite structure, how these things takes place. That will give you a better, much more idea. So this is to show the formation of diffuse double layer or Stern layer. These two sides, so you can consider that these are the two clay platelets. Once it comes in contact with the water, it forms some kind of a crowding of different ions. So if you have got the negative clay platelets are considered to have the negative ions. Then positive ions which are present in the water or the surrounding media, they will come because of the attraction of opposite ions. The next layer, if you have the positive ions, then when it comes in the with the water will also bipolar. It will become H plus and OH minus. Again, another level of OH minus will come. This way, it will form a diffuse double layer. Okay. And that is how the expansion takes place. So to give you an idea, the surface area of normal soil, you will find it is maybe 100 meters square per gram or so. For monzonite, the surface area is 800 meters square per gram. So if you explain in the layman's term, if you take 1 gram of monzonite, you can spray it to a 800 meters square of area, similar way. It is actually very, very active clay. Now this compacted buffer system, when we are talking about the high level lowest canister, it has got very complex phenomena which is going on. As because this is a faculty developed program, so I am talking a little more about the detailed research which we do, or which as a geotechnical engineer is. So far I was giving the overall idea. Now this is a schematic picture of the actual scenario. If we consider this as the high level lowest canister, and opposite side, if you take a cross section of what we have here. So here you have got the high level lowest canister which radiates heat. That heat actually flux goes to the post rock gradually. And from the rock, if it is 500 to 1000 meter below, mostly it is expected that it can have the saturated condition. So, and this is where the bentonite block is there. In the bentonite block, you can see you find one side a high temperature, another side low temperature. The low temperature side, due to the presence of water, you will have high water. Other side, you will have the less water. So water will try to flow from opposite side to the canister towards the canister. Temperature will flow from the canister side to the opposite of the canister. And in between, what will happen when water is entering, the bentonite block also will try to expand. But because here expansion is not allowed, one side you have got the rock, another side you have got the canister. Both are rigid material. So as expansion is not allowed, it will try to apply pressure. And again, if the water is flowing, it will also take away some of the chemicals. So what are the things we need to look at? The swelling pressure which is developing. If there is change in a chemical property due to the flux in water, how the saturation inside the blocks is affecting, and how much time it takes this temperature to flow from here to here, that depends on the thermal conductivity. Also that depends on the water content. So these are the various properties we need to look at inside a bentonite block. So we're looking at the temperature flow, which we call as the T. Here you can see an example of highly coupled and complex THMC problem. So altogether, this bentonite blocks is under thermal condition. H is for hydraulic, where water flow is taking place. M is mechanical, where it is undergoing expansion, or so it's exert the swelling pressure. If it is exert the swelling pressure, for example, towards the canister, you have got the more water content, it will try to expand more. Whereas towards the canister, there is high temperature, it will try to shrink. Okay. So inside this cell shell, one side you may have more pressure, another side less pressure, which is the mechanical component. Also, due to flow of the water, there may be change in the chemical compound, which is the C problem. So this is in engineer term, it is called as the THMC problem: thermal, hydraulic, mechanical, and chemical problem. So when we use anything like in geotechnical, if we say, when you test some soil, we determine liquid limit, plastic limit, shrinkage limit, specific gravity, or we do in the field SPD test. We follow certain guidelines, right? We use Indian standard codes or American codes or PS different codes. Similarly, for this case also, such kind of codes has not been developed, but SKB, which is the agency for waste disposal program of Sweden, their guidelines is considered now highly regulated, or they have done a lot of research. So when you try to choose this bentonite material, certain parameters or minimum property which we need to ensure, that is taken from their reports. such as hydraulic conductivity should be of the order 10 to the power minus 12 meter per second. So in case the normal clay, we get around 10 to the power minus 11 or so. Here you need to have minimum, let's try 10 to the power minus 9. For sand, it is 10 to the power minus 6. We need to achieve around 10 to the minus 12. So normal clay in using normal compaction, it will not affect. So what you have to do, you have to compact more. So that's why this normal proctor compaction is not useful in this case. Static compaction is done. Static compaction means you take the specimen ring and place the soil, whatever you want to prepare, specimen ring or mold, whatever, place below a compaction machine and apply high pressure to achieve that compaction level. Okay. It is compacted of the order 1.8 gram per cc to 2 gram per cc, etc. Then it should exert a minimum swelling pressure of 1 megapascal. In normal pressure, when we go for, let's say, consolidation pressure, we talk about maximum 800 kilopascal. But this property must be there to have at least 1 megapascal of swelling pressure to ensure self-healing capacity. And the hydraulic conductivity is to limit the transport of the diffuse dominant process. So if you allow more water to flow, there are a lot of chemical and other flow will take place. To limit this, you require this. The maximum temperature, always try to keep around 100 degrees centigrade to ensure that buffer retains its properties for a long period of time. That means this is a clay, highly swelling clay. If you expose it to very high temperature, for example 300 degrees centigrade, the main mineral of bentonite is the montmorillonite. So if you expose it to up to 300 degrees centigrade, it can be converted into elite or some other material. So there, all these less hydraulic conductivity and swelling property, all these things will not be maintained. These are some more properties. So mostly we focus of this hydraulic conductivity, swelling pressure, temperature, and thermal conductivity properties. So density here you see it's at least 1.6 kg gram per cc or 1650 kg per meter cube. And it should be less than 2.1 kg per meter cube in order to limit stresses on the canister and the rock movements. Because if it is very high, the higher you compact, when it comes to water, it will expand, try to expand more. As the expansion is retarded, it will exert more pressure, and this can actually cause rock failure in the nearby places, or the canister itself can break. Okay. So these are the different methods, engineering processes. Ultimately, we look at THMC, thermal, hydraulic, hydrogeological or hydraulic, mechanical, and chemical processes. This tables to show the various type of bentonite and what are the different properties. These are the not only geotechnical property, you will see that some properties which are chemical as well. So we call it physicochemical properties. Specific gravity, mostly it's varying from 2.65 to 2.8. The liquid limit, you can see for the difference, you can understand why it is expansive clay called. Normal soil, you will get the liquid limit maybe up to 60. Well, here it is varying from 172 to 474. Okay. So this Indian divalent and Indian sodium bentonite, what we are talking about, this is the test conducted in our laboratory at IIT Patna itself. The bentonites are procured from Rajasthan itself in the Bikaner and Barmar area. These two districts, you have got a lot of such expansive material. Then total specific surface area. this is where you see it is 550 to 600. Then cation exchange capacity. This is another property where you have got the different, whether it is sodium type of bentonite or calcium type of bentonite, or these two mostly dominant for all sorts of bentonite which is available. If it is sodium type, usually that is got high soiling type. If it is calcium, relatively less soiling type. So, as we said, that this monolite can expand a lot, and as the expansion is not allowed, it will try to apply a pressure, and that pressure is known as the soiling pressure. And as geotechnical engineer, before designing such a disposal facility, we need to make sure that it should fulfill the criteria of less achieving the soiling pressure given by the regulatory authority. It is fulfilling the hydraulic conductivity criteria, so we need to test the hydraulic conductivity in the laboratory, as well as it should not exceed the soiling pressure, which can cause problem. So what we can do, we can if we take the soil specimen inside the specimen ring, compact it. You can see in this picture, this is the specimen ring which is here, and this is the compacted specimen, okay, which is 10 mm height. At bottom and top, there are two porous discs. This is more or less like a odometer, or where we do the consolidation test, those who are aware of. Then we place the water is supplied from the bottom, or it can be supplied from bottom and top as well, but this should be maintained up to the top height of the soil specimen so that it becomes saturated gradually. So once you prepare the specimen, place it in the odometer. This is a specially designed, usually it is not available in the market mostly, so you have to design it, and this is what we have developed for our laboratory. On top of the podestone, you put some kind of plunger, okay, and you keep a load cell. So here you see this is the specimen. As soon as water is coming, it will try to expand. As expansion is restricted, it will apply pressure, or it will try to push this place. As soon as we are trying to push it, at the bottom it is restrained, at the top here it is restrained. In between you have got the load cell. The load cell will give you the reading, how much load it is applying. So if you know the load, you can divide by the area, you can find out the pressure. So this is one of the aspect. Now you can use for BTech and MTech project. There are many projects can be done. For a single type of bentonite, you can use water, you can use a different chemical solution, how this soiling pressure is varying. Then you can use the different temperature, some maybe 100 degrees, some 80 degrees, some 50 degree temperature. You can apply some heater here. Okay, so different tests can be done, and also different range of compaction and compacted specimens to be used to find out which is the best suitable one. This is the real life picture when the test was going on. You can see this is the specimen with odometer, which is completely covered. The water level is maintained through this. This is the water where it is there. This is the load cell through which we measure the soiling pressure. And this is the specimen ring. You can see how it looks like. This is MX80 bentonite, which is mostly planned to be used in USA, Sweden, all those countries. It is mainly for Wyoming in USA. So unlike the normal compaction you do, the specimen ring itself is very small. It's like like the consolidation ring. So you can place the bentonite powder or the soil inside, to press it from the top in a statically compacted way, the amount of compaction you want to achieve, And after compaction, you can find out the this height, the diameter, you can find out the volume, take the measurement of the weight, you can recalculate what is the density that is achieved. Now these are some of the results to show for different density, different type of bentonites at different temperature, what happens to the thermal effect, how this is to show how the hydraulic conductivity varies, and also here it is shown suction. Suction is nothing but, you can say, the negative pore water pressure, because bentonite is highly expansive clay, or it has got a lot of negative charge. It can attract a lot of water. Even if you leave it in the normal room temperature, it attracts the moisture from the surrounding area, and you will find some amount of water is there. So how these properties are changing, these are some of the typical results. This is also some of the results for change in water content at different location. It is a reported result of after 18 years, how the water content varies at different locations. Initially, I showed one picture where you have got a large compacted block and you have a heater at the center. The test was conducted by FEBEX, or you can by Spanish organization, and these are their results. So in deep, I am not going on detail all these results. Then you have got the electrolyte condensation, or that means if you have got different salt solutions, these results we have published recently. How this soiling changes so far in the field. When you get some amount of water, you don't know what will be the exact concentration. So you need to study for different range of salt solution. It can be vary up to 1 normal to the 0.5, 0.3, etc., and how those things varies. How the liquid limit changes, how free soil index changes, all these properties are part of the research of this proper material. So this kind of test, using this odometer, what we can do, we can mainly test for soiling pressure, we can test for hydraulic conductivity, we can test for consolidation, but finally it is under the complex phenomena of THMC or PHM behavior, where both temperature is applied, water also is applied, and you measure the different parameters like change in hydraulic conductivity, change in soiling pressure, thermal degradation of temperature, etc. So this is one of the device which I used during my PhD time, or it was actually manufactured at Cardiff University and developed. And you can see this is the compacted bentonite block, which is 100 mm by 80 mm in height. And we placed a heater here, which we can apply the temperature up to 100 degrees centigrade. There is a temperature controller through that. And this is the plunger. There is a load cell. From this, there is a chamber here. Through the inlet, we fill it with the water. So you can see that exactly, if you 90-degree rotate it, you can say that this is the representative of the field application, where you have got the canister temperature here, and the water is percolating from the rock on the other side. And it can exact pressure, it can temperature will vary, all those things can be measured. So in between, we close different sensors. These sensors give us the temperature and the relative humidity. So with time, we monitor how this temperature and relative humidity varies. So from this relative humidity and temperature, we can calculate the suction. And at the top, we measure the variation of soiling pressure. So after test was conducted for 3 months, 6 months, up to 6 months test was conducted, how this moisture content varies at different level, how the temperature varies in different level, or how the chemical properties varies in different level, and how the soiling pressure also varies. All these tests are done. These are done known as the THM behavior. But we can do the test maximum 3 months or 6 months. So in order to ensure, also there will be a challenge of scale factor. Here you cannot do such huge amount of big specimen you cannot prepare, and same condition cannot generate. All these challenges are also there. This is actually the picture when the test was conducted. Earlier was the schematic diagram. So these are the sensors. You can see the load cell through which pressure was calculated, soiling pressure. At the bottom there was a heater. So this heater jacket was kept so that temperature uh, loss is minimized. And these are some of the results at different depth when we measure the temperature, how it varies. So in a 22 centimeter difference itself, the temperature between 2 points is around 10 degree varying. And from the temperature and relative humidity, this equation actually gives RT by M ln RH gives the suction. So suction also can be calculated, and that can be plotted. So this is the relative humidity, how it varies at the different places with the depth and with the time. So the test, 3-4 tests are conducted and up to 180 days, that means 6 months. This is the result of the soiling pressure which was measured from the top and how it varies with time. Okay, so this is, I can say in briefly, what are the different type of test we do using this material and the research which can be done in terms of the geotechnical engineering. And then, so far, whatever I have focused on is mainly on the experimental work. But all these experience are you can do maximum for 3 months, 6 months, etc. But that is to use some kind of numerical model. Now everything is on numerical because of the pandemic. So that numerical model will give you a assurance for 300 or 500 years whether these parameters which we are using will be fulfilling the criteria. Okay. So the another aspect is doing the numerical model. So you can feed a model, use those parameters and see how it is happening, whether these properties which we want of the buffer material is remain same for 300 years or not, whether it is changing, whether the chemical property is changing. After ensuring this only, we can go for the actual disposal. So there are a lot of still research is required. So that's it from my side. I don't know how much I am able to convey. So any question, please ask. Thank you.
Thank you, sir. I have a question.
Yes, please.
Sir, instead of bentonite soil, is there any material that we can use around the canister?
No, actually, because of it has got this unique property of low hydraulic conductivity and self-healing. Bentonite is the globally, you can say, throughout the world, as chosen as the best material. If some more research can be done and some material can be found out which fulfills the same thing, as I said, uh, what is called concrete or cement mortar, those also has the less permeability or less hydraulic conductivity. However, it has not be it cannot do the self healing. Let's say there is any crack formation takes place, it cannot heal itself. But in case of bentonite, if the water is coming in, it automatically heals those gaps. So that is why so far it is chosen as the preferred material, and every country is planning to use. In case it may happen that within next 20 years some other material we can develop. Research may go on that direction also.
Okay, sir. Thank you.
Yes, any more question? Okay. Okay. Thank you very much. Thank you for the opportunity. Thank you. Thank you very much.
Thank you.
So we can log up now. Okay. Thank you. Thank you.
Thank you, sir.